MapReduce optimization. So we were in the middle of MapReduce, and we know that we break a job into multiple tasks, okay, and the tasks are scheduled before the reduced task. So basically we had 100 files in our previous example, right? But if you don't have 100 processors, you can do it on 10 processors, but you will have 10 map cycles. Alright, so the number of processors does not have to be equal to the number of map jobs. The map jobs actually in both cases are decided by locality of the data. Wherever the data is, that's where you have to generally schedule the job, but you could do it in many cycles. And then the reduced jobs are also done in parallel. Now it is not necessary that you finish all the map jobs before you start reducing. Alright? And so people who are doing research in this area, they are basically saying what is the right way to schedule all these things. Okay, so that is not, that is where the expertise lies. That's where the different companies or different people will solve the problem differently, because they will have a different number of map, reduce, and when they start, how they schedule them. So all that is optimization. Alright, synchronization. The map jobs should be comparable so that they finish together. Now it is not necessary, but if you have one job which finishes after 100 units and everything else has 1 unit, then 99 units somebody is waiting for nothing. Right? Either the map jobs cannot be assigned, new map jobs cannot be assigned, or reduction cannot be completed. So you really need to divide. So when you do key value pair, and you have to say, well, you handle these two keys, you handle these two keys, or you handle these 20 keys. You should divide it somewhat so that they're approximately same number, same amount of time. Alright, so you should have some idea of how big the job is, and that is how you should do it. And code and data co-location, we already talked about that you should put the map jobs. Now one of you can go and get the handout. Map jobs and where the data is. So one thing is that in the Google file system, the difference between the Google file system, or actually in this case HDFS as we will call it in a minute, Hadoop file system, is that the data is not over there. The data is right here with the processors, local disks. Remember when we talked about data centers, we talked about storage area networks. So there was a place where everything is storage, and then you have fiber channel coming in to your processor server. Well, that was then. Now basically it's better to keep that data you're processing right local. Right? So there are local disks, and so the jobs that are assigned, they are assigned accordingly. Either you have to move the data, which you could do, either you move the data or you assign the jobs to where the data is. Any question about that?
So,
yeah.
So each of these map modules or reduce, they are basically servers with storage.
They are virtual servers with storage. They are servers, but they could be virtual.
Virtual servers.
Yeah, they could be virtual, but the storage is local, right? And fault and error handling. If a processor fails, basically you will know by timeout or things like that, or no hellos, then the task needs to be assigned to another processor. So that is kind of clear. Is that you generally assign to more processors than you have jobs, and some jobs, so that way if you really want to do it, make sure that you don't have to wait longer, then you can already assign two processors to each job, and both of them are doing the same thing, or 3 processors to each job, and all 3 are doing the same thing. But as soon as one completes, we are done. So there is a lot of performance optimization which is required here. All right. So, any question about anything on this slide? Yeah.
So maybe it's not on this slide, but does it does it work like mostly distributed hash tables?
Does it work most like a distributed hash table?
Yeah, like doing ring for each server.
Ring.
Yeah.
Okay, there are no rings here. All right. So distributed hash tables work very differently. I mean, I wouldn't go that here because that is. I mean, you know it, but everybody doesn't know it. So I'm not going to explain that right now. So it's not like that. In the distributed hash table, there is no master in the first place. Here, it is centralized. So there is no need for P2P communication, peer-to-peer communication. The slaves, I mean, in this case, we call them, the names are coming up in the next slide, I think, or maybe they were in the previous slide. Names are coming up in the next slide. So they are task nodes, they don't talk to each other, generally. I mean, they don't need to talk to each other. They just need to follow the master. Okay, your question.
Yeah, I have a question. So can you give me an example of when the process is failed and the here last the same?
Yeah.
Can you give us an example?
Okay, so let's go back to our previous example. The question is, what happens if the processor fails? So you have 100 files and you have 100 processors. If a processor fails, you will get 99 results and one you will not get. Right? So you will reassign it to somebody else, or you could have just divided the 100 files into 50 files and 50 pairs, and you give 2 files to each of the 100 processors. Understand what I am saying? You give 2 files to each of the 100 processors. So you have now created 200 jobs, even though there are only 100 jobs. Right? So there is one level of redundancy right there. If one processor fails, somebody else is doing the same thing, no problem.
Why the processors fail? Because
They are cheap processors.
oh, okay. Too heavy to.
Well, these are not. Okay, so generally in the data centers or in the old data centers, people used to buy special Xenon processors, right? Not processor that you and I use at home. Right? So those are expensive. But these are not those expensive processors. These are cheap processors. Cheapest one that anybody makes. And so they can fail. Same thing for the disk. These are not really, hi-fi disks. These are cheapest disks.
So fails means here the processor can make it in time, the specific time, right? The processor can make the computation in the certain time.
Okay, so your question is it possible that some processor is so slow? So that will not be called as failed. Okay, if the processor is slow, then the master will know that this processor is slow and let me give him half the job. See what I mean? So that part is understood. The part is not predictable is failure. Something unexpected. Disk can fail, job will not be finished. Right? All right. So, okay. So we are done with the optimization. Now we come to Hadoop. Story of Hadoop. How did the name Hadoop come in, first of all? Hadoop is the name of a toy elephant that belonged to the inventor's son. All right. Basically what happened was Google published these 3 groundbreaking papers. Yahoo noticed it. And Yahoo said, let's implement this stuff. So Yahoo started implementing it. And the person who was implementing, there were 2 people, Doc Cutting and Mike Caffarella. And they called it something. And then when they saw these names, they said, okay, let's just use the same thing. And then they used the elephant toy, which was Doug's son's name, Hadoop, and they called the project Hadoop. So this was Yahoo Hadoop. Right? By the way, there is one page common. So from the previous handout, you take out the last page, throw it away, and you will start. This slide 617 will start. Right now, we are still in the old handout. So story of Hadoop is it's a toy elephant name. All right, and these guys went ahead and started a company called Cloudera, which is very popular and famous right now. And Hadoop went to public domain, Apache. Now Apache has many projects, as you know, and so this is now called Apache Hadoop. It's open source, so you can download it, we can download it, anybody can download it and use it. Apache Hadoop, and that's the official symbol of Apache Hadoop. Yeah.
What is the role of Cloudera in Hadoop?
I'm sorry, Cloudera?
What is the role of Cloudera in Hadoop?
Role of Cloudera?
Yeah.
Or they are just companies which are supporting. Okay. So basically nowadays, whenever you have open source software, you need support. Even though it is open source,
Okay.
you need support, right? So Cloudera actually does more than support. They provide support. If you found to start Hadoop today, you don't have any expertise. They will teach you classes. You don't have any other software that goes around it. They will provide you that software. If something goes wrong, they will come and fix it. So their support.
Something like what Red Hat used to Linux.
Have you heard of Red Hat Linux?
Yeah.
So what does Red Hat do?
Support. They have their own distribution.
They have their own version of it, which is maybe a little bit ruggedized. They take the public domain code and fix few things here and there. Sell it to you.
Cloudera has a product called CDH, which is Cloud.
There's plenty of examples of open source support. So the world is moving in that direction. Is that the software itself is open source, and we will have hundreds of examples in this lecture of different things that are required. It's all open source, but people support it. Some companies support it.
So Cloudera, they have their own version, like Apache.
They have what?
They have their version of.
I'm not sure. You will have to go to Cloudera and figure it out. But they are the leading companies because they were the first one to start. They were the people who knew Hadoop before anybody else knew Hadoop.
Cloudera has something called CDH, which is Cloudera distribution of Hadoop. What it does is it takes the open source Hadoop and it tracks it around management software around it to make it easier for deploying it on a cluster and managing that cluster and so on.
Right. So the answer was that Cloudera does have a version which has the core, which is Apache, plus something else to manage it around. If you want to instantiate some, MapReduce servers or masters and this and that, you need management,
Yeah.
and that comes from Cloudera.
Okay.
Any other question? So Hadoop. Hadoop is an open source implementation of MapReduce framework, and basically it consists of three parts. There is a common package, which are all the files we need to start Hadoop. Then there is a distributed file system, which is I'm going to describe in a minute, and then the MapReduce engine, which I'm going to describe one more time in a little bit more detail. So now HDFS. HDFS is Hadoop Distributed File System. Very similar to Google File System. It requires data to be broken into blocks. Each block is stored on two or more nodes on different, and then there is a central master server which is called the name node. Name node exactly knows where the blocks are and what the names of those blocks are. Names means if you have a file system, whatever it is, then you need to translate that into a block number. Once you know the block number, then you need to know which disk has those block numbers. So that is why you have two maps, a block map and a name map. Yeah.
So does it mean that the name node also didn't store the real data? Does it mean that the name node here actually didn't store the real data?
Redundancy. The name node is what?
The name node here didn't store the real data.
Oh, it doesn't store anything. Yeah, it doesn't store the data. It stores only the map. Yes, metadata. Yeah.
Other than the fact that this is a name versus a master, is there any other differences?
There might be some minor thing, but overall there is this is same idea. Okay, that's why they call it HDFS and not GFS. Okay, so the name node manages the file system namespace and keeps track of where each block is, and then as before, when you want to write something, you come to the name node, it tells you go here, this and that, all that goes on. The file system is maintained as before. Now there are a few more nodes. So there are job tracker, so data node, job tracker, and task tracker. Data node basically are the workers. Those are the people who are doing the map jobs and the reduce jobs. And they don't sit idle, they just go to ask the master, please tell me what can I do for you. Now, if they don't come and ask, then they are sick, and so you have to replace them. But they keep coming asking, and that is actually those requests are also used as what they call liveness detector, that they're live. And so that is data node. Data node also have data, by the way, right? That's why they call data node. Job tracker is the one that assigns the map jobs to the task tracker nodes that have the data or are close to the data or in the same rack. So task tracker and the data node, they might be same. So as shown in this picture, they are same actually. Everywhere we see DN plus TT. So the data nodes are the data and the task trackers are the task people who are doing the task. And so generally they are the same, and you will have many of them. And then there is a job tracker which assigns that. It says, okay, you do this key value pair, you do this key value pair. So mapping is done by the job tracker. Now the task tracker keep the work as close to the data as possible. So basically the task tracker wants to be close to the data node, and so as shown here they are same. So anyway, so now let's see. You have switches, you have job tracker, name node, secondary name node, and then there is a client node. I am not sure what the client does. Probably it takes the results at the end. I am not sure at this time. So anyway, so everything else is clear, right?
So
Yeah.
the job tracker, is it in the master server, or is it in the name node?
Where is the master server?
What is the job tracker? Is it in
Job tracker.
Is it master or this?
Okay, so there is a separate function. Okay, one more thing you should understand is that whenever we talk about any of these are functions. Right? You can put them anywhere you want. You can put all of these in one node, one CPU, and you are done. But job tracker is different than the name node. The job tracker's job is to assign the jobs. Right? Name node job is to keep track of the storage. So name node is storage manager. Job tracker is computation manager. Make sense? You can put them all in the same CPU, but those are functions. Packaging is your choice. On one CPU you could create 10 VMs. One VM does the job node, one does the name node, one does DNPT, and maybe 5 do DN and PT, and so on and so forth. You can do whatever you want. Or you can put all of them in one physical processor. You don't have to have VM. You could have one physical processor which also does job tracker, name node, data node, everything. Right? In that case, you would not get any parallelism at all because everything is being done in serial. But if you divide this into pieces, you can divide any way you want. So these three functions are clear. Doer, assigner, and basically computation doer, right? So basically the DN and TT, data node and task tracker, they go together. Now, data node gets the data if necessary, do the map function and write the results to the disk. So their job is, data node, as their name says, is basically try to get the data local. The job tracker then assigns the reduced job to the job data node that have the data close to them, and all data has a check attached to it to verify its integrity. What that means is all the data has a CRC field in it. Right? So when you get a 64 kilobyte block, you can be assured that it is all correct because somebody has done this redundancy check. Now, Hadoop is a big family. Much of this family comes from Apache. So first you have the Apache Hadoop. When you get the Apache Hadoop, you get those three pieces we talked about. You get a MapReducer, you get a file system, and you get the common package. But there are alternatives for the MapReducer. Another alternative is called Yarn, Y-A-R-N. Okay, I was looking for the acronym for Yarn and I couldn't find it anywhere, so this is just Yarn. But I would think that this is yet another reduce something. YA generally is yet another. Okay, but I'm not sure what yet another RN is. But so that's an alternative to MapReduce, and that basically, so they call it MapReduce version 2. Apache Mahout. You know what is a Mahout? Mahout is this guy, little guy sitting on the top of the elephant.
Where does that come from?
It's an Indian name, by the way. This is an Indian word. And I don't know how it got here though. So in Hindi language, Mahout, right? Subharti? Right? Mahout is Indian. Elephant trainer. So that Mahout is a package, Hive is a package, and then there's a pig, and so on and so forth. Now let's go one by one. So Mahout is the, okay, I can see why, machine learning algorithm. So this is basically, a lot of mathematics in there. So whoever probably developed it must have, whatever it is, Asian, whatever nationality, Asian, this thing. So they have put this name Mahout. Mahout is machine learning algorithms for collaborative filtering, clustering, classification, all of the mathematics that you can do there. Hive. Hive is the data warehouse infrastructure. Okay. What is the data warehouse? So data warehouse are the people who supply you data. Suppose you want to get stock market data. Where do you go? Anybody? Anybody has stock market stock? Nobody? Where do you go for stock market data? Okay, Yahoo is a good example, but I would go to Fidelity. Right? They are what we call, and actually behind Fidelity there is some other company that supplies the data. So those are data warehouses. Those are where the data is stored, and they charge you for supplying this, right? So similarly, this is the data warehouse facility for Hadoop. You can get the data summary, you can get the query, you can analysis using SQL language like HiveQL. So this is a package. If you get that, then you can put it on your, then you can just use it. People can use it. This is just the interface as a data warehouse. Pig. Pig is the platform for creating MapReduce program using a high-level language called Pig Latin. All right, and similar to SQL. So now I didn't define SQL so far. Sorry, SQL is actually coming up later on, so I'm going to define it now. SQL is the structured query language. It's called SQL, by the way. Okay, you can call it SQL, you can call it SQL. It's a structured kernel language. So the old days, when people had the structured information only, they had databases called relational databases. They had a language using which you could manipulate those relational databases. Right? That language is SQL. So now that we don't have any more restructured data, now that we don't need to use SQL, we use Pig with Hadoop, not with everything else. With Hadoop, you use Pig. And then you can extend this language by Java and Python, etc., etc. By the way, how many people know Java here? Okay, let me ask you the opposite question. How many people do not know Java? 1, 2. That's it? Did I count it right? Those 2 guys, you have to learn Java fast. Because our lab requires Java. Does it require Java? Yeah. We have a lab on MapReduce, which requires very little Java, not too much. So Java, Python. You can extend the Apache Pig with Java, Python. Okay, next.
YAN stands for Yet Another Resource
Yet another
Negotiator. Resource Negotiator.
Yet another resource negotiator. YARN. YARN. Yet other resource negotiator. Apache Avro. Avro is the data serialization system, and the Avro ideal is the interface description language syntax for Avro. So basically, here's the thing. I am just putting one line, but if you go to the books on big data, there is one chapter on Avro, one chapter on HBase, one chapter on every of these lines that we are here. We don't have time for that kind of thing. So I just wanted to be familiar with the name and rough idea of what they do. If you ever have to do any of this, you will have to read those chapters. And I have given 2 references. One is, if you go to Apache website, they give you a little bit of documentation and everything else and download pointers. Or if you go to Wikipedia, they give you some description. Okay? But here we are just going to get by with one-liners each. So now let's see if we can make sense of this. Avro is the data serialization system and interface definition language, IDL. Interface definition language is the interface description language syntax for Avro. So that doesn't make much sense. Basically, all it is saying is that they have their own language and you can serialize the data. So data serialization system. Basically, when you have things, they may not be in key value pairs and things like that. So you have to convert that into, so that you can then start giving it out to different map jobs, map servers or whatever. So that is the data serialization. This is just manipulates the data from whatever form it comes into the form where it can be manipulated. HBase is a full database, and this is a very famous database. So if somebody says you know big data and if they don't understand HBase, then they don't know anything. So basically that's why these names are very important. You need to know these names. HBase is the DBMS, the database management system. It is non-relational. Again, I should probably put the relational first. The next slide is going to define what is relational. But this is a non-relational database, part of the Hadoop project, designed for large quantity of sparse data. So the good thing, the difference about HBase is, first of all, it is non-relational. Second, it is designed for sparse data. The other relational databases, which were used so far in the past, they were all designed for dense data, where every line, every row had all the columns. Here, some rows have some columns, and some rows are mostly empty, with 1 or 2 columns. That is why it is called sparse. Right? So this is designed for sparse data. It is non-relational, and provides a Java API to access the data used by Facebook. So basically big companies are using all this software. Obviously, since Hadoop was developed by Yahoo, they are using all of it. Facebook is using it, and Amazon and everybody, you name it, they are all using this now. Zookeeper is a configuration service, synchronization service, and name registry for large distributed systems like Hadoop. So if you have a 2000 node Hadoop cluster, you need something to manage it. Zookeeper. Zookeeper keeps track of all the animals in the zoo, right? Cassandra is another distributed database management system, highly scalable. So you can see on Hadoop they already made two, HBase and Cassandra. Ambari is a web-based tool for provisioning, managing, and monitoring Apache Hadoop clusters. So this Ambari looks like, I was just thinking there is some overlap between Zookeeper and Ambari. This doesn't say distributed, so maybe this is for small clusters, whereas Zookeeper is for distributed clusters, large clusters. Chakwa is a collection system. So we talk about data serialization system. Data serialization, it takes the data from here and makes it into divisible parts in the collection system. But you want to collect the data before you serialize it. For that they have a system here, Chakwa. Scoop for transferring bulk data between structured databases and Hadoop. So what is Scoop? Scoop is Hadoop plus SQL. SQL is the data that you can use to, SQL is the language that you can use to get data from the old databases, which are relational databases, which are structured databases. Now you want to put them into Hadoop, you can use Scoop. And this is somewhat, in some sense, there is some overlap with serialization and other things. So basically you take that structured data and put it on the Hadoop file system, and that can be done by Scoop. Uzi is a workflow scheduler system. So this is where the scheduling comes in. When you have 10 processors to run, 10 jobs to run, things like that, you schedule, okay, you will reduce, when you will start reducing, things like that. Actually they will start reducing only when the jobs finish. But even that part has to be scheduled as to, who basically, since there is so much parallelism, who will listen to whom and when they will start. So Uzi keeps continuing. This is a big community. Accumulo is this sorted distributed key value store based upon BigTable design. So this is actually in some sense similar to HBase and Cassandra, and whereas I think those things are full databases. These are basically, this looks like it doesn't say full databases, but it's a key value store, and so it is similar to BigTable. BigTable is a database too, and so is HBase, and so is Cassandra. So this is the third database, and this is the third most popular no SQL by column system. Now I am getting into trouble because everything that you need here is in the next slide. So I am going to go to the other slides and come back to these things because the slides are out of order a little bit. So I am going to come back here and then go back to this place. First of all, databases are of many types. Okay, first type of database is a relational database, and relational databases actually they store data in tables. Okay. So for example, you could have order table. In the order table, you will have order number, customer ID, product ID, quantity, and unit price. That is how the orders are coming in. You keep filling in this table. That is your order table, right? And this is a relational database. There is a row and there is a column. Row is each order, column is details of that order. Right? Customer table. Customer table has a customer ID, customer name, customer address, customer gender, customer income range. So now if you want to find out which customer placed which order, what you have to do? You have to look at the customer ID here and the customer ID here and then take a join of that. Right? Then you can figure out which customer bought when, what, how much they paid. So this is a relational database stuff, and see the relational database basically have a schema. They store data in table and they have a schema. Schema says for order table we have 5 columns and the columns are these. And for the customer table we have 5 columns again, but they have different names. So this is called a schema. Schema is basically the definition of the table. Okay? So this is the relational database, and then they have SQL, the language, which is the most commonly used language for creating, retrieving, updating, and deleting. Creating if you want to create a new customer or new order. Retrieving if you want to retrieve, so is writing and reading. Updating, changing, and deleting, removing it. Right? This is called CRUD. For CRUD, you use SQL. For example, if you want to find out the gender of the customers who bought XYZ, what you have to do, you have to select customer ID, state, gender, and product ID from customer table and order table where product ID is XYZ. So first of all, you find out all product ID XYZ, then you find out all the customer ID corresponding, then you go here and then you find their genders. Right? So basically relational databases, they use relational algebra with things like join, intersection of sets. Basically you have sets here and you join them, intersect them, and find the answer. So non-relational databases are called NoSQL. No stands for not only. Not only SQL. So any databases that use non-SQL interface, they are called NoSQL. You can use just C, Ruby, Python, any language for retrieval. Typically the data is stored in key value pairs. So then you don't need SQL. So there are a whole variety of NoSQL databases. And they are not limited to rows or columns. Data structure and query is specific. So they don't need tables. They are very high performance in-memory databases. So what does in-memory means? There used to be time when the memory was in short supply, you needed to read into the disk to find the data. But there are many databases which for today's standard, there are many databases which don't need the disk. You can just keep them in the memory. You have 8 GB of memory in your computer. You could have 16 GB of memory and the database is smaller than that. You can just put into the memory, you can get it fast. And that is what is used in many real-time applications. When you want to make a phone call, the telephone company doesn't go and read your record on the disk. They have it in the memory. Right? Anywhere you need things in microseconds and milliseconds, you can use in-memory databases. And they use RESTful APIs. So that's another word you need to learn. RESTful. REST stands for representational state transfer, which has no meaning whatsoever. If you read the word representational state transfer, it doesn't say anything. What it is they have the same interface that the web has. Some of you who have taken 473, which none of you have taken, the first lecture we give you HTML. In the HTML, you have 4 commands: get, put, and something like that. There are 4 commands, 4 or 5 commands. HTTP, not HTML. HTTP. Hypertext Transfer Protocol. So when you want to get something from a website, you use HTTP. And so you send a get command. You can say get www.csc.boostall.edu/Jain. It will give you that page. Get command. And so there are commands like, there are 4 or 5 commands, very simple commands. If you use the same commands for any other place, that is called REST API. Somebody came up with the nice idea in a PhD thesis. There's a whole PhD thesis. That is basically what we should be doing. Use the HTTP API for everything else. So these things are also similar. When you want to get an object, you say get me this, put this, or thing like that. Okay. So that is called RESTful API. And they don't offer ACID. They offer base. And we already learned ACID means atomicity, etc., and base means eventual consistency. The keyword is consistency. The database may not be consistent right now, but within few minutes it will become consistent. Right? So there are plenty of NoSQL databases now. Okay? Then there are new SQL. Well, the SQL guys were not behind. They said, well, the old SQL you are comparing, new SQL is better, but new SQL is even better. So the new SQL guys are SQL, which takes care of the problems with the old SQL. By the way, before I go to the old SQL, one of the most popular SQL packages was MySQL. What is MySQL? MySQL was a package which I think was developed by, I forget the company name. Was it one of the Oracle's previous son? I don't know. So anyway, it was now it belongs to Oracle. And so MySQL is a package that I think is now in public domain or open source or whatever. So, and most people use MySQL. If you are using SQL, you use MySQL package. And so, but it has limitations, because of relational databases and because of SQL, whatever it is. So they come up with a new SQL databases which extend SQL's life and extent. They have the same performance as NoSQL, but they use SQL. They provide ACID, and they are also called scale out SQL, which means that they are scaling out, they are making SQL bigger, and by generally using distributed processing as opposed to doing centralized processing. All right. So now we learned 3 words: SQL, NoSQL, and new SQL. Any questions about those 3 words? Right. The 4th word we understood was RESTful API. RESTful API means web-like API, HTTP-like API. Yeah, exactly. So the new SQL is still using relational databases, but they are saying relational databases can be fast too, they can be bigger too, they can be everything by distributed processing. Right? So they are structured data still.
Is it also in memory database?
In memory is a special case of either one. In memory there are orthogonal direction. You could have in-memory SQL, you could have in-memory NoSQL. You could have in-memory new SQL, but I think new SQL is designed really not for new in-memory stuff. It is designed for big data, so generally it would be distributed in many computers, right? So I think this probably will not be ideal for in-memory. By the way, every computer that you have, every iPhone that you have, every smartphone that you have has a database inside it, and which is based upon one of these SQL stuffs, either MySQL or NoSQL or NewSQL. So this is very common. Databases are very common. They could be small, they could be big, but you need the whole package. Your computer has a package. Your laptop has a package, because everywhere there are databases. All right. So then there is a column databases. You can call them columnar or you can call them column oriented. And the idea was that the previous relational databases, they were row oriented. Okay? Row oriented means how you store the data. So if you have a relational database, they will store the whole record. So for example, let's just talk about your Outlook contact list. When they do it, they will do it in a relational database, and with your name or with your contact's name, their job, phone number, blah blah blah, everything will be stored one after another in the memory or in the disk. So that is row oriented. All right. People say no, that is not good. Why is it not good? So for example, let me first, before I say why it is not good, let's just take this example. So this is 3 columns and actually 3 rows as well, but this will be stored as follows. First, 101 is Smith 10,000, then 105 zones 20,000, then 106 zones 15,000. Like this it could go thousands of rows. Right? This is row-oriented storage, right? Now, what is good about this? That you can find all the information about a person. If you want to find out Smith everything, you have it in one place. You just do one read and you got it. Right? Because everything is in the same place. It's also good, but it is difficult to find out how many people have the salary between 10 and 15K. You have to read the whole database. Because no one place you have that column. So if you ask column-oriented question, then the row is no good. If you ask a row-oriented question, row is good. But if you ask column-oriented question, then it's no good. Now, here's the thing, why we need column-oriented question? Because when you have big data, you are really not interested in any one person. You're really not interested in any one event. You are really interested in the whole overall statistics. And that is column-oriented. Right? You want to find out how many people have name Smith. You don't want to find out Mr. X Smith. You just find out how many people have name Smith, or how many people have salary of this, or how many people are male, female, blah, 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 right? So those are all column-oriented questions. So when you want the overall statistics, those are all column-oriented questions. So they are not done well by the row-oriented storage. So what you do is you store column-wise. That's all you do. So you will store like this. 101, 001, 105, 106. So these are the keys and these are the values, which are the record locations. These are the keys, and Smith is the key value pair, key value pair, key value pair. Okay? Now, if somebody asked you how many people have the salary between 12K and 15K, all you have to do is not read any of this stuff. You just go straight to this place and read this stuff and find out. You don't have to read the whole database. Second good thing is that if you wanted to add one more column, it's very easy to do in this one than to in that one. In that one you have to rewrite all the records. Here you just write one more record. Alright? So this is easy to get column statistics, very easy to add columns, and good for data with high variety. High variety, we simply add columns, when things change. Alright, so column database is new stuff, right? So now we go back to one more slide here. Is that, so we talked about relational databases, and now in relational databases, the most common database is PostgreSQL. Then there is SQLite, and MySQL. These are the names of the databases. Alright, NewSQL, we already talked about those. Then there are non-relational databases, which would be key value pair, and there are databases such as React. Document databases such as web pages, etc. There are MongoDB and CouchDB are examples of those. Columnar databases, where the database is stored in columns. HBase is an example of that. There are graph databases, which store nodes and relationships, which store graphs. Why do you need to store graphs? Anybody knows? Any example of whether you really need to know the graph? Nobody?
For search, right? You do the graph storage, then you can do faster search. Is that
what search?
Find a search tree.
Search tree, yeah, I know, but where do you use graphs?
Where you use graphs?
Yeah, in databases.
Maps.
Social networking.
Okay.
I'm a friend to you, and you are friend to him, and he is friend to whom, and then we want to find out, how many people are in my whatever number of relationships, right? All that is graph, and there is a lot of graph databases now. Right? So there are graph databases, and then a special kind of graph is spatial databases. Now spatial, when you do a map, that's also is a graph. St. Louis is next to Kansas City. Kansas City is 20 miles from some other city, and so on and so forth. That's a graph right there. But it is spatial, and it's for map and navigation, so there are databases just for that. in-memory data, you don't have to remember all these names. By the way, I won't expect you to remember, but at least you should know what is a spatial database. You should know that. You don't have to remember that port GIS is relational. Yeah.
Because this, just now I mentioned, this graph database.
Yeah.
This is really used in the social network nowadays.
Yeah.
Is it really used?
Yeah. So these are used in social networks, yeah.
Facebook.
I don't know which one Facebook, which particular database they use. They may not use Neo4j,
Okay.
but they have some kind of graph database among themselves. LinkedIn has their own. Everybody who has to do anything with the social networking will have a graph database.
Okay.
And that's how they can suggest you who should be your friend. You remember when you log into Facebook, they tell you, can you want hear suggestions? By analyzing those graphs. So in-memory databases are all data in the memory for real-time applications, and cloud databases, everything is in the cloud. So anyway, in the cloud, you could have three kinds of things. You could have IaaS, infrastructure as a service, which means all they give you is a virtual machine, nothing more. VM image, they could give you the whole image with the database code, everything in that thing right there, or they could do database as a service. Database as a service means they have the whole thing for you. All you have to do is, just give them your query or whatever, and then they have implemented Hadoop and whatnot, everything for you. So anyway, what I want you to do is know the blue stuff. If there's any question about any of the blue stuff, ask me now or ask me in the next class. But that you should know. You don't need to know these things. Any question about any of the blue stuff, all these names make sense to you. Okay? All right. If it all makes sense to you, then we can go back to where we were. I think we finished. We got stuck here in a scoop. I think we did a scoop. We did Uzi, Accumulo. All right. So Thrift is another interface description language, basically another name for API, to create services using many languages. So this basically allows you to write your service by C, C++, Java, Perl, Python, Ruby, etc. So this is just the API. It converts those languages into whatever is required below. Beehive is a Java application framework to allow development of Java-based applications. So this is designed especially for Java. And Derby is another database. Now we already saw three so far. So we saw a database called HBase. Then we saw Cassandra was a database. And then third one is Derby. Now Derby is Relational Database Management System, RDBMS, Relational Database Management System. That can be embedded in Java programs. It's very small, only needs 2.6 megabyte disk space and supports Java database connectivity and SQL. So there are many things which go along with Apache Hadoop, and each of these actually is lot of detail which we won't get into this class, but if I was teaching a class on databases or big data or anything like that, then we would go each chapter by chapter on those things. Now, if we get out of Apache, then there are some non-Apache tools. Cascading. This is open source software abstraction layer for Hadoop. It allows developers to create a jar file that describes the data, source analysis and results without knowing MapReduce, and Hadoop jar files contains the cascading jar file. So basically what you do is, you don't need to know Hadoop, you just create your cascading jar file, you learn cascading, you write your jar file there, and then you put that with your Hadoop jar file, and then you can submit it to wherever Hadoop is, right? Storm is an event processor. And this is very similar to what we saw before, a scheduler. Okay? And that scheduler was Uzi. Alright? So there is a Storm. Is open source, event source processor, distributed computation framework for alternative to MapReduce, allows batch distributed processing of streaming data. So the thing about a Storm is that it allows streaming data to be analyzed. Then there is EMR, elastic MapReduce, which is automatic provisioning of the cluster, naming, etc., etc. So that is basically, actually it says also known as Hive. So if it is same thing, then why we have another name? I don't know. Hypertable. Hypertable is another database. So we saw so many so far. So Hypertable is in addition to Derby and so on and so forth. Now, Hypertable is, it doesn't say whether it is RDBMS or key value pair, what it is, but these are the tools that go along with Hadoop. Now there are without Hadoop tools. Without Hadoop, actually they ended up on this slide. Either they were not Apache, they were not open source. So there's something called Fuse, file in user space, file system in user space. So generally the file system space stays in the kernel space. So when you want to open a file, you just tell the operating system to open the file. Operating system knows where it is, and then you go and manipulate it, read, write, whatever, delete, and the operating system does all the things for you. So that is called operating file system in the kernel space. Opposite of that is file system in the user space, where you can do whatever you want to do with the file system. So the users can create their own virtual file systems, and this is available for Linux, Android, OS X, etc. Cloudera Impala. So Cloudera is the company we talked about. They have a product called Impala, which is the query execution on HDFS and Apache. So basically, a lot of people already have a lot of SQL code because they had a relational database before, and they had written that, okay, to find this, execute this code. So there's a lot of SQL code. Now, if they come to Hadoop, then they can use Impala. So that is the SQL query on Hadoop file system and on HBase. Then Map or Hadoop. This is again similar to Cloudera Hadoop. This is another company. MapR is another company which provides enhanced version of Apache Hadoop, and I had to put this here because it is very popular. It is used by Google, EMC, Amazon. Right? And Big SQL is IBM. Again, this is SQL interface to Hadoop. So this is like Impala. And Hadoop. Hadoop is the analysis of massive data sets using SQL with Apache Hadoop. So basically, again, the third SQL interface. So SQL is very popular. There is a lot of code available. All we have done with Hadoop is we have changed how we compute it. So that's why all these interfaces are selling. Big SQL, Impala, Hadoop. These are all basically SQL on Hadoop. Okay, so let's just see. Yeah, that's all basically. So all this is that there is a lot going on in databases. This is a course on networking, and I didn't just want to, we cannot talk about networking much actually until we understand all these words. If you don't understand SQL, if you don't understand relational database, if you don't understand key value pair, column databases, it's difficult to talk about big data. All right. So hopefully after this lecture you know some of these words. Okay. So now we talk about the last thing, and that is analysis. The third part of the big data is what techniques to use. Mathematics. Remember mathematics, that Mahout stuff. And that is this slide. So analytics means anything that you do to analyze, to discover the pattern in the data, and you might use statistics, programming, operations research, any of these two techniques, any analysis technique you use to somehow make some useful information out of it, then it is called analytics. So analysis is mathematics, but analytics is, just after mathematics, you do something which is people can use, some information that comes out, patterns that comes out, some result that comes out that anybody can use. So that is analytics. All right. So SQL analytics would be whatever the people were doing in the days of SQL, which means they could count, you could get the mean, you could get OLAP, which is online analytics processing, something like that. So basically whatever you could do online in the SQL days. Now, there are three kinds of analytics: descriptive, predictive, and prescriptive. Descriptive means past. Predictive means future. Prescriptive means recommendations. Okay, so let me just go one by one. Descriptive, if you analyze the data and you tell me that, well, the mean is so much, that the variance is so much, all that is descriptive analytics. All you described me the data, you didn't really do anything other than just describe me what is already there, past. Alright? Predictive, if you use that and then you say, well, I think next year the sales would be 2,000, that is predictive. Right? You take the past and use regression or something else to predict. Right? Prescriptive is that you give me a prescription, a medicine, which says now, from now on, when a customer comes, please do this. Greet them and say hello. That is prescription. Right? Prescriptive is suggests decision options, continually update these options with new data. As new data comes in, and that also includes prescriptive analysis might also include things like your suggestions. When you go to Amazon and they suggest you a book or something else to buy, that is prescriptive. All right, data mining. Data mining is basically, in some sense, finding the patterns, trends, and relationships. Generally using clustering. I don't know how many of you know clustering, but basically if you have some data, you could make several groups out of that data and say, well, this group belongs to people who have income of that, this group belongs to people who have generally roughly income of 10 to 20,000, and their preference is to buy only books. These people are millionaires and they generally buy big cars or whatever. So that is clustering. You cluster groups, right? So that is what is done. That is not the only thing, but basically that is one of the key techniques in data mining, and there are other things. Simulation, you all know what is simulation, so I'm not going to describe that. Then optimization, linear or nonlinear optimization, and machine learning. Machine learning, basically, some of you are already taking courses, so you know more than I do. But basically the idea is that where you learn from the data and then use it. Okay? So you have a sample, empirical data, and then you use those things to predict for the other. Okay, so you have, in machine learning, there is a learning part in addition to analyzing part. All of this is analytics. Alright, if nothing else, you should have learned 4 words today: analytics, prescriptive, descriptive, and predictive. Right? And descriptive means describing past, predictive means prediction, future, prescriptive means prescribing, means telling me what to do. All right. Now you can apply analytics to anything, and whenever you apply to something, they call it data analytics. So there are people who do web analytics. They analyze the web pages. Learning analytics, they analyze learning processes. Data science, now it's a whole field. There's a new field called data science, which is basically the whole, everything else is, this data analytics field is called data science. So if you graduate in data science, you are going to learn all of these techniques. Maybe they will teach Hadoop, I don't know. They might teach you databases, but they teach you all the analytics. All right, I think we finished everything then. So we can go to the summary. So 5 key points. First of all, big data has become possible due to low cost of storage, high performance server, high speed networking, and new analytics techniques. See, so 5 years ago we did not know MapReduce. Maybe, I don't know, maybe it is more than 5 years ago. But anyway, few years ago, 10 years ago, we didn't know, how to break up the jobs and things like that, right? So we have this new analysis techniques, new analytics could also include machine learning, etc., etc. Okay, so the other part comes here. The MapReduce comes here. Second thing is that the 3 papers from Google File Systems, BigTable, and MapReduce, they sparked the whole development of Apache Hadoop. All right. And the key components of the Hadoops are, these are the components, and I could put them in blue, or basically these are the things that by now you should probably memorize. HDFS, what is that? File system, right. And this is the Avro, is the data serialization system. MapReduce or Yarn. Yarn is yet another. Huh? Yeah. Yet another what? Negotiation, yeah. This one. Okay. And then Pig is the language. Hive is the data warehouse. HBase is the database. Zookeeper is the reliable data compression. Now these are actually, among all the names that I had before, these are actually the key, in the sense that these are more, like basically each of these, as I said, is, basically is a big chapter in the books, and there might be even books on these. So actually there might be a book which says Introduction to Zookeeper. Okay? Obviously there's a book on HBase, there's a book on Pig, I know, there's a book on whatever. So these are all big topics. Then discovering patterns in data and using them is called analytics. It can be descriptive, predictive, and prescriptive at least, right? You know that. The type of the databases could be relational, and then you have SQL databases, means relational databases, right? Then you have NoSQL. NoSQL means not only SQL. And then you have NewSQL, and then you have key-value pair, you have document databases, column databases, graph databases, and spatial databases. All right, that's all there is among the reading list. What I have done this time is I have put also the references. Now, references are not something that you should read right now. You don't need to, but these are the things that if you ever do any research, or if you ever to do, for example, Google papers, you can live without them. People have already read them and put them into Hadoop, so you need to read about Hadoop. So those are references there, and even the Apache websites, if you need ever, then these are references. But what you do need to read are these. Okay? So start with this first book, which is a Safari book, and few papers here, and then the second last book. Okay? And generally when I have a reading list, please start from the top. I try to put them, best first. Okay? So whenever you read, start from here and then go down.